In this video, we're going to briefly introduce and visualize the breadth-first search algorithm. Breadth-first search is a method for enumerating all the nodes in a graph. When you don't know the complete node or edge set, we imagine ourselves wandering or exploring through a graph that is really, really big. And indeed, this is what happens many times when we're collecting graph data. Rarely do we have a map of the entire graph, but we might be wandering through a page on the internet or through a piece of physical infrastructure or a social network. And we can look nearby and say, hey, who are the neighbors? What's close to me? And by doing this algorithm, I can gradually assemble a picture of the entire graph. So here is a graph on which we'll do breadth-first search. And here is a description of the breadth-first search algorithm. So breadth-first search is an algorithm that works on any graph, not just trees. But as we'll show in an exercise, if you look at the nodes and edges that are followed by breadth-first search, you actually will be able to produce a tree associated with the graph, even if the original graph is not a tree. So rather than walk through all the steps on their own, what I'd like to do is I'd actually like to run breadth-first search on this tree, or sorry, on this graph, in order to visualize what's going on. So the first thing that I need to do in breadth-first search is I need to pick a node U to be my starting point. I'm going to pick this one right here. Then, in the first line of breadth-first search, I'm going to add U to what I'm going to call the frontier, which can be represented as a data structure with a Q. I'm just going to put a little dot beside my starting point U to represent that node U is currently on the frontier. Then the next thing I have to do is represent that U has been visited. So I'm going to mark U as visited, and so I'm going to gray it out here. U has been visited. Once I have visited a node, I then enter this while loop. Okay, so while the queue is not empty, and guess what? It's not empty because there's one item U in it right now, one thing on the frontier. Well, while the queue is not empty, I'm going to grab the top element of the queue. So in this case, that's V. And I'm going to pop U off the queue. And so once I'm done operating this, I'm going to erase this mark here. It's going to no longer be in the queue. And what I'm going to do is I'm going to take all the neighbors of that element. So if this is the node I'm currently operating on right here, this is labeled U, but it's also my V in this loop. I'm going to look at all the neighbors. So I have 3 neighbors here, 1, 2, 3. What I'm going to do with those neighbors, I am going to add them to the queue if they're not already visited. And indeed, none of these neighbors have been visited. So because they have not been visited, I'm going to add them to the queue, and I am going to mark them as visited. So these ones have all been visited as well now, and they're all in the queue. And then once I'm done with this operation, this iteration, I'm also going to remove the node V from the queue. So I've branched out, and now I have a new frontier. I'm all done with my original node U. Now, since I've completed one of these outer loops here, I go and I pick another element of the queue. So let's say that we are going to pick this element right here. So what I do now is I go again, I look at all the neighbors of that element. So this element has 3 neighbors. However, my if statement says only operate on the neighbors that have not been visited. So in this case, this neighbor has been visited, this neighbor has been visited, this neighbor has not. And so the only thing I need to do is I need to mark this neighbor as visited, and I need to add this neighbor to the queue. And furthermore, I need to take the node I started with in this iteration and erase it from the queue. Now I keep going. Okay, so I'm going to consider this neighbor or this node in my queue that's also on the frontier. Guess what? When I take this node off the queue and I look at all of its neighbors have been visited. So I'm going to do this loop, but none of these if statements are going to execute. The only thing that's going to happen is that after I'm done operating, I'm done with that node on the queue. My frontier is clear. Okay, let's do another one. Let's look at this node here. This node is on the frontier. Okay, I look at all the neighbors of this node. There are 4 of them, but this one and this one have already been visited. And so when I do this if statement, nothing is going to happen. There's 2 neighbors that have not yet been visited. And so for these 2 neighbors, I'm going to add them to the frontier queue. Okay, and I'm going to mark them as visited. And I'm going to remove my current node from the queue, all done. And then I have 3 more nodes on the frontier if I'm continuing my loop because my queue is not empty yet. But guess what? None of them have unvisited neighbors. And so I'm going to execute all of these steps, but actually nothing is going to happen except that they are going to be popped off of the queue. And now I'm done. I have no more elements in my queue. And so I have explored my entire graph. There are many, many applications of breadth first search, many applications that we can choose. You can use this algorithm to find shortest paths in graphs, for example, or to locate an element. Now, I did want to illustrate the fact that I claimed down here, that the nodes and edges followed by breadth first search form a tree. If we check what edges we followed, and I should have been marking these along the way, but let's take a quick look here. If we check what edges we followed, we started with U, and we followed this edge to get a neighbor, this edge to get a neighbor, and this edge to get a neighbor. Then we went over here, we followed this edge to get a neighbor. When we visited this node, we didn't visit over here because that one had already been visited. And so we did, and actually, indeed, this one had also been visited. We didn't have anything to do. Then up here, okay, we visited this edge, followed that edge to get a neighbor, followed that edge to get a neighbor. So if you look at all the edges that we followed during breadth first search, we actually formed a tree, and it's possible to prove that this will always happen. The set of edges that you follow during breadth first search forms a tree, and if you want to form a tree that covers a graph called a spanning tree, you can use breadth first search to do it.